Chapter 9, Section 3, Hypothesis Testing by Correlation and Regression. Correlation and regression analysis are popular methods for hypothesis testing. So, we need to know how to perform hypothesis testing using correlation and regression analysis. Moreover, we need to know how to interpret the results based on various metrics. Let's recap the process of hypothesis testing. First, specify null and alternative hypothesis. Second, set the significance level. Third, compute test statistic. And finally, determine whether we can reject a null hypothesis using p-value. Remember that while a null hypothesis says that there's no difference, an alternative hypothesis says that there's a significant difference. So, what does difference mean here? Difference between what and what? In a hypothesis testing using correlation, we test whether the correlation coefficient equals 0 or not. So, the null hypothesis should state the correlation coefficient is 0. And the null hypothesis should state that the correlation coefficient is not 0. In a real case of hypothesis testing by correlation analysis, a hypothesis says that A and B are positively or negatively correlated. And if we can reject a null hypothesis, we can support this proposed hypothesis. We should know that correlation is not causation, so we cannot identify A and B as the cause or the effect. Similar to what we do in a case of correlation analysis, in a hypothesis testing using regression, we test whether the regression coefficient equals 0 or not. So, the null hypothesis should state that the regression coefficient is 0. And the alternative hypothesis should say that the regression coefficient is not 0. In a real case of hypothesis testing by regression analysis, a hypothesis says A positively or negatively relates to B. Here, A is the independent variable and B is the dependent variable. And if we can reject a null hypothesis, we can support this proposed hypothesis. Some researchers propose a hypothesis which says A increases B, or A positively affects B in a regression analysis. However, we should know that regression does not confirm a cause and effect relationship. Even if you use variable A as the independent variable and B as the dependent variable, and we obtain a significant relationship, we cannot conclude that A is the cause and B is the effect. The result of a regression analysis only tells us that A and B are positively related. As the second step, set the significance level, that is, the probability of committing type 1 error. Type 1 error refers to an error where we reject a null hypothesis when it is actually true. If we set the significance level to 5%, it means that we reject a null hypothesis if the possibility of committing type 1 error is estimated to be lower than 5%. In the next step, compute test statistic, a statistic used to test the hypothesis by transforming data into probability distribution. By computing test statistic, we can compute p-value to make conclusion in the final step. In correlation and regression analysis, we compute t-values as test statistic. In the previous sections, I said that correlation coefficient tells us the correlation strength. However, strictly speaking, it is not true. We also need to consider the p-value because we need to consider both effect size and statistical significance in correlation analysis. In some cases, in particular, when the sample size is small, the correlation coefficient can be a product of chance. If we observe positive or negative correlation with a large sample size, the correlation is probable. But even if we observe strong positive or negative correlation with a small sample size, we are not sure whether the correlation really exists. Suppose our dataset has only 3 observations and 2 variables, x and y. As shown in the scatter plot, each data point are located on a straight line, so the correlation coefficient is almost 1.0. But it may be a product of chance. If we obtain these new observations, the correlation coefficient can be much lower. So, even if the absolute value of the correlation coefficient is large, the correlation is not statistically significant if the p-value is larger than the significance level. In the left plot, the correlation coefficient is high, but the p-value is larger than 0.05. So, if we set the significant level to 5%, we should regard the correlation coefficient as 0 in this case. And even if the absolute value of the correlation coefficient is small, the correlation is statistically significant if the p-value is lower than the significance level. In the right plot, the correlation coefficient is smaller than in the left plot, but the p-value is lower than 0.05. So, we should say the correlation coefficient is not 0. Similarly, in regression analysis, we need to consider both effect size and statistical significance. That is, we need to check both regression coefficient and p-value. Even if we observe strong impact of the independent variable on the dependent variable, we are not sure whether the impact is statistically significant or a product of chance. So, even if the absolute value of the regression coefficient is large, the impact is meaningless if the p-value is larger than the significance level. And even if the absolute value of the regression coefficient is smaller, the regression may be meaningful if the p-value is lower than the significance level. So, in the left plot, the regression coefficient is minus 0.654, but its p-value is 0.229. So, if we set the significance level is 0.05, the effect of x on y is not significant. So, we should regard the regression coefficient as 0. In the right plot, the absolute value of the regression coefficient is smaller than in the left plot, but its p-value is 0.005. So, the effect of x is statistically significant, and thus we should say that the regression coefficient is not 0. Thank you for watching. Please thumbs up and subscribe to my channel.